My name is Farhad Najafnia from Babel University of Technology, and together with my co-authors, Professor Ramin Hashemi and Ehsan Dorchepour from Iran University of Science Technology and Dr. Ali Fazli from Imam International University. I will present our study entitled Effect of Material Formability Parameter and Cutting Method on a sheared edge stretchability in advanced high strain steel sheets. Okay, as you know, advanced high strain steel or AHSS are family of lightweight automobile steel, including dual phase steel or DP, transformation induced plasticity or TRIP, CP or FB steels. The combination of soft matrix and the hard second phase, like martensite, provide high stretch while maintaining excellent global formability, as presented by elongation, However, strain localization at a soft and hard phase interface lead to poor local formability and promotes premature edge cracking during stamping in parts like seat rails or float side panel. Premature edge cracking in AHSS forces automotive manufacturers to rework parts, leading to increased manufacturing cost. So, to quantify local formability edge stretching capacity, the hole expansion test is commonly used. To reduce manufacturing cost, understanding key parameters governing hole expansion behavior is essential. Okay, in this study, we examine how material deformation parameters such M value or R value or M value and different cutting methods like laser or water jet can affect edge stretchability capability of AHSS. Using digital image correlation for full field strain measurement, we also provide corresponding microstructure interpretation. First, we perform comprehensive hole expansion test on DP 590, DP 980, TRIP 980, SPFC 440, and DC 06 steel with the hole prepared by laser, water jet, and EDM cutting method. All tests followed by ISO 16630 standard using constant punch speed of 1 millimeter per minute. In this method, the punch expand the existing hole until the first crack appear. To account for a spring back after unloading, the final hole diameter is measured using DIC and a different verified by CMM method. This spring back effect significant in AHSS but negligible in a conventional steel like DC06. The hole expansion ratio defined the standards formulation was then calculated and reported for all materials. And on this slide, you can see the hole expansion setup, including punch, die, blank holder, and punch geometry and dimension. The specimen before and after testing, the specimen geometry, dimension, and CMM measurement setup. Okay. After that, to measure the formability parameters such as yield strain, ultimate strain, elongation, N value, R value, even M value, a series of uniaxial tensile tests were conducted over a wide range of condition in accordance to ASTM E8 at crosshead speed of 1 millimeter per minute. To accurately capture the displacement and strain field during the test, DIC optical measurement system was utilized. On this slide, also you can see uniaxial tensile test setup, a specimen before and after testing, and a specimen geometry and dimension. Okay. The results show that DC06 and SPFC 440 specimen achieve a hole expansion ratio of approximately 168 and 155 respectively, while the DP 900 590 specimen reached only about 103% before the onset of crack initiation. This clearly highlights the lower edge stretchability of DP 590 material. On this slide, you can see the Vickers hardness of pyrite is approximately 3,125, whereas the martensite phase exhibit much higher hardness, around 622. This significant hardness contrast is key microstructural characterization of dual phase steel. This large hardness mismatch result in increased local dislocation density and dislocation pileup at a pyrite martensite intersection. This stress concentration locally rise strain and facilitate premature crack initiation during deformation. As observed in SEM image, crack initiation and early crack coalescence occurs preferentially at a pyrite martensite phase boundaries. This microstructure observation confirm hypothesis that the phase interface stress concentration govern the crack initiation mechanism. Okay, the hole expansion ratio HER or HER of DP 918 and TRIP 918 were approximately 53 and 50% respectively. Additionally, a difference in HER between DP 980 and TRIP 980 can be attributed to the trip effect. The trip effect refers to the transformation of return austenites into martensite during deformation. Therefore, the trip effect is activated in TRIP 980, localized straining increase, leading to faster edge crack and reduce in HER. Okay, and last page is conclusion. Okay, the pronounced pyrite martensite hardness difference causes severe dislocation pileup in a ferrite, leading to delamination at their interface, as you can see in SEM pictures. Additionally, it can be stated that difference in HER between DP 918 and TRIP 918 steel can be explained by trip effect. The mechanism that TRIP has and DP doesn't have. The increased M value along with trip effect tend to reduce edge crack resistance and promote earlier crack initiation at shear edge. The presence of pronounced micro crack on the whole surface of water jet and laser cut of DP 519 specimen contribute to their interferior edge stretching. And this is the valuable conclusion that you can use for designing a stage when you work with AHSS family. And this is the reference page. Thank you for attention.